Good morning, class. Today we'll be doing lesson 2.2b, the standard normal distribution. I actually like this picture. I thought it was kind of funny. You're probably like, Mrs. Byrie, you need a life. Unfortunately, for today's lesson, I'm unable to put video screens of me in the video, but that's because I'm having to do this at school in order to get this video out quickly. So we'll make this as quick and painless as possible. I hope that you enjoyed the one with my face in it, which I thought was kind of fun. We'll try it again at another time. All right, so let's talk about the standard normal distribution again, which we've already been talking about. And remember, we talked about this as a normal distribution with a mean of mu, whoops, I'm so sorry, mu, and a standard deviation of sigma. And if a variable x has a normal distribution, remember here's our name for the normal distribution, with a mean of mu and a standard deviation of sigma, then the standardized variable is z. And what was z again? Well, you guys should remember this. It's x minus the mean divided by standard deviation. Now we're using different symbols here because we're talking about populations, but it's all right, it's the same thing. But in a normal standard deviation, normal distribution, so sorry, we do use mu to represent mean and sigma to represent standard deviation. Now another key vocabulary term is the standard normal table. The standard normal table is found in the back of your book. It's table A on page T2, and this is a table that we will be using. If I give you a test, I will have this table copied off for you, because you will need to know how to find the area under the standard normal curve with the table. In addition, next class, well, not tomorrow, but Thursday, I believe, we will be learning how to find the standard, the area under the standard normal curve by using our calculators. But first we have to use the table. So the standard normal table is a table of areas under the standard normal curve. The table entry for each value, z, which remember is our standardized score, is the area under the curve to the left. And this is key because this is one of the biggest mistakes people make, to the left of z. When we look at the table, and I'll show you in just a moment, people often try to go to the right. So be very careful here. It's always to the left. To the left, to the left. Okay, never mind, I won't sing. So here is an excerpt from a table. This is not the entire table. This is a short one. You'll notice in your book it's 2 pages long. But here is a table, and we want to find the proportion of observations in a normal distribution that were more than 1.53 standard deviations above the mean. Now remember, and even in the picture here, it shows us that we have all of this is the area to the left of z. Now I want to know more than 1.53. And what I'm going to suggest to you is that you draw a graph. And this is actually a really great suggestion for AP exams, because if you draw a graph, it's easier for you to see. So just sketch it. So I'm going to sketch myself a quick graph here. La, la, la. My graphs are never very good. Here is mu, and I've got 1, 2, 3, negative 1, 2, 3. So this is 1, 2, and 3 standard deviations away. Now, I want 1.53. So that looks to me like that's going to be right about here. But I want it more than. So I'm wanting to know, what is this area up here? How do I find this area up here? Well, in order to do this, I'm going to need to use my chart to find the area to the left, and then I'm going to subtract it from 1. Because remember, the total area under a standard normal curve is always equal to 1. So let me show you how to use our chart. Now, we want 1.53. So we're going to go find our z-score. Here's our z-score. Aisle right here, z-score. And what we want to do is we want to find 1.53. So let me show you how it goes. On the z's, you're starting at 0 and you're going up to 3.4, which is usually the max you're going to get on a table. After that, it's so minuscule that we don't have much to work with. the other side, you'll get the other page, which is the negative numbers. But we're interested in 1.53. So you are going to get your ones and your tenths in this row right here. And in this, in this column right here. In this row across, this is your hundredths. Now, obviously, you're going to use your brains. If you have 1.536, you're going to go kind of halfway in between 1.53 and 1.54. It's nothing big. You're just going to use some logic to use your reasoning in order to find the correct term. But right now, it's pretty easy. We want 1.53. So we go down here and we see, okay, 1.5 is right there, and 0.03 is right there. So if I take my pen and I go down this one, and I go over this one, I should get my answer. So the area to the left of 1.53 is 0.9370. And I apologize about the writing. I know that my writing is not that great, but I'm using a different stylus in order for you not to be annoyed by the clicks. All right, so that's the area to the left. So remember, that represents all of this area. Okay, so 0.9370 is that area. Now, in order to find the area in black that we're looking at, remember we're going to take 1, because that's the total area. We're going to subtract the 0.9370. And we will get 1 minus 0.9370 is 0.063. These O's don't look good. Sorry, that's an O. All right, so hopefully that makes sense. Using the chart is the most confusing, and then determining if you have to subtract it from 1 or leave it as is. So this is a fairly difficult question. An easier one would be for me to ask you, what was the proportion of observations less than 1.53? And then you could just use the table and say, well, 94% were less than 1.53. All right, so now we want to find the observations from the standard normal distribution that are between negative 1.25 and 0.81. So if you go back and use the chart that we used before, we would find that the area to the left of 0.81, this is the area to the left of 0.81, is 0.7910. And the area to the left of negative 1.25 is 0.1056. But I need to find this area in the middle. So whatever shall I do? Well, it would stand to reason that if I take 0.7910 and I subtract 0.1056, then I should be able to get the number that I'm looking for, which should be 0.6854. Now, there's other ways that you can do that, but that seems to be the easiest one. Part of the key to finding these areas is to remember to figure out what you subtract from what. Do you subtract it from 1? Do you subtract it from another number? If you draw a sketch, though, it's always easy to see, because you can see I can overlap this 0.1056, which is right about here. So basically, I just want to get rid of that. So if I know this whole total, I can just get rid of that much, and it gives me this answer right there. Okay, so let's find the proportion of observations from the standard normal distribution that are between 0.58 and 1.79. All right, so I'm going to draw a few graphs here, sketching some graphs. Oh, those are really ugly. 3, 1, 2, 3. This is 0, 1, 2, 3, 1, 2, 3. All right, so between negative 0.58. Well, negative 0.58 is somewhere right around here. So that's this area here, to the left of negative 0.58. And then 1.79 is going to be somewhere up here, 1.79. Now, I'm going to use my chart, and you should be getting your charts out and using them to practice. If we go to 1.79, if the z is 1.79, then the area to the left is 0.9633. If I have a z-score of negative 0.58, the area to the left is 0.2810. So again, we want to chop this area off. We're trying to take this off and get rid of it so that we're just left with this area. So we're going to do 0.9633, and we're going to subtract 0.2810. And if you put that into your handy dandy calculator, or you do it in your head, you'll find that the area between negative 0.58 and 1.79 is 0.6823. Now we are going to use a calculator to learn how to do this on the calculator, but for right now I want you to do your problems and your sample problems by using your chart in your back. You need to get good at using your chart in your back, and we'll even be using them backwards here in a bit, although I don't think I put that on the thing, so that would be interesting. Alright, standardizing and using the standard normal table. Statistics problems demand consistency. And what do I mean? This is our 4-step process, right? First we state, then we plan, then we do, then we conclude. Every single time. So this is our 4-step plan. So, whoops, sorry guys. So in order to solve problems involving the normal distributions, state, express in terms of x, plan, draw some graphs or pictures so you have an idea of what to do, and then you're going to perform your calculations. And the calculations that we're going to be doing for this section are primarily going to be standardizing scores, and then we're going to use the tables to find the area under the curve. And then we're going to write a conclusion. Because remember, statistics is wordy. In 2008, in the 2008 Wimbledon tennis tournament, Ralph Nadal, I never say his name right, averaged 115 miles per hour on his first serve. I don't want to get hit by his tennis balls. Assume that the distribution of his first serve speeds is normal with a mean of 115 and a standard deviation of 6. About what proportion would you expect to exceed 120 miles an hour? Alright, so first we're going to state. First, let x equal speed of first serve. And it has a normal distribution with a mu of 115 and standard deviation of 6. So the second part, to plan. I'm going to draw myself a picture. I want to know where x is greater than or equal to 120. So the first thing I want to do is standardize 120. Turn 120 into a z-score. So 120 minus 115 divided by 6 equals 5/6, which is 0.8 0.83. So I am looking at an area under the standard normal curve. If this is mu, 1, 2, 3, 1, 2, 3, I'm looking somewhere right about here, and I want to know this area above the curve. Great, so this is 0.83. So the third step that I'm going to take is to do. So I'm going to, oh well, I already did, but I'm going to use the use the table, and I'm going to look up 0.8, and then at the top I'm going to go 0.03, and then I'll get a number which happens to be 0.7967. If you're having trouble reading this chart, come see me. So I know that the area to the left, all of this, is 0.7967. So to find the area above 120, I do 1 minus 0.7967, and I get 0.2033. And now I'm going to conclude. About 20% of Nadal's first serves will travel at more than 120 mph. And that's all there is to it. All right, so a little bit more difficult problem. What percent of Ralph Nadal's first serves are between 100 and 110 miles per hour? So remember, we're going to first let x equal the speed of first serve. Let's change colors to black. And we know that this distribution has a mean of 115 and a standard deviation of 6. So I'm looking, I want the proportion of 100 being less than x being less than 110. That's where I'm looking. So now step 2, I'm going to plan it out. So here's my picture. And I want to know 110 and between 100 and 110. I'm going to go ahead and standardize these scores because I like to, I know that this is 115, so I know it's going to be somewhere down here. But let's go ahead and standardize 100 and 110. So Z for 100 is 100 minus 115 over 6, which is negative 2.50. And the Z-score for 110 is going to be 110 minus 115 over 6, which is negative 0.83. So if I go back over here to my drawing, 1, 2, 3, so this is negative 3 standard deviations away. I know I'm looking at an area between here. Sorry, I didn't draw that very well. And this is not quite 1. So I'm looking at this area right here. So now I know I want the area under the normal curve where negative 2.50 is less than Z is less than negative 0.83. Same thing that I wrote here, except I've standardized it. Okay, step 3, we're going to use the chart. So first we're going to find out the table. We're going to look at Z at negative 2.50. The area is 0.0062. And when Z is negative 0.83, the area under the curve is .2033. 2033. So we are going to take the point, remember we're going to take this one, which is my negative 0.83, and we're going to subtract this one, we're going to subtract this in little junk here that we don't want, which is the negative 2.50 to get the answer. So I'm going to have 0.2033 minus 0.0062, and I get 0.1971. So my conclusion is about 20% of Nadal's first serves will travel between 110 and 115 miles per hour. Now, if you would like some more questions that cover, to go over a couple more questions like this, go to page 120 and 121 in your textbook, and there are questions about Tiger Woods. And you can see the answers and how they are worked out there. Now, we can also use table A in reverse. And when we use table A in reverse, we're going to take an area and then go back in order to figure out the X value. So we're first going to find out a Z-score, and then we'll take that back and find the X value. So high levels of cholesterol in blood increase the risk of heart disease. For 14-year-old boys, the distribution of blood cholesterol is approximately normal, with a mean of 170 milligrams per deciliter of blood and a standard deviation of 30 milligrams per deciliter. What is the first quartile of the distributions of blood cholesterol? Well, first of all, what are they asking us? First quartile? Really? They can't just say that? No, they can't. So quartile 1 is asking for the area that's 25% or 0.25 of the normal curve. Okay, so I know the area, but I don't know the Z-score. So in this case, what I want to do is I am looking for a curve that has a normal curve of, what was our mean? 170, 30. And I want to find 25% of that curve. So that's step 1. Step 2 is to make a plan. Well, here's the plan. I'm trying to find all of this little area here. And I know it's 0.25%. But I need to figure out what is the Z-score for 0.25. So what you're going to do is you're going to look, so step 3, do. You're going to look in your chart, and what you want to find is the entry closest to 0.25. The entry, remember this is the middle of the chart, closest to 0.25. And it's actually 0.2514. So you find 0.2514. And then from this, if it were in your chart, you'd have 0.2514 in your chart. You'd go this way and you'd go up. If you go this way, you're going to find that it corresponds to negative 0.6. And if you go up, you're going to see that it corresponds to, I'm going to put this in red, 0.07. So if you use your chart, you can find that the Z-score is negative 0.67. Negative 0.67 is the Z-score. Now, I need to convert that. So I'm going to convert it back. So remember, it's z equals x minus mu over standard deviation. So in this case, it's negative 0.67 equals x, which I don't know, minus 170 divided by 30. Now, if I do that, I'm going to move this up a little bit. Whoops. Move this up so I have a little bit more space. All right, so if I do that, I'm going to negative 0.67 times 30 equals x minus 170. So if you work all that over and then you add your 170, you get, well, here, let me just do it by hand. Negative 0.67 times 30 is negative 20.1 equals x minus 170. Add your 170 both sides, and you get x being 149.9 equals x. So, what do I know in my conclusion? Again, I'm going to move this up a little bit. My conclusion, step 4. I'm going to conclude that the first quartile of blood cholesterols in 14-year-old boys, remember being very specific, is about, I'm going to round this, 150, what was it, milligrams per deciliter. There you go. 4-part process, all solved. Now again, we're going to learn how to do this with the chart going forwards and backwards, and then also there's a calculator button we can use. All right, so the last little bit we're going to look at is this data close to normal? Is this close to normal? Now, I have already drawn a histogram, and you know, if I kind of superimposed a curve over it, it's not too bad. And I've got my summary statistics with my mean of 8.682 and 2.225. So, and I gave you a bunch of data. So really what I want to know is, am I close? What can I use to tell me if I'm close? What have I learned this chapter? Well, one of the good rules that I have learned is the 68, don't forget your 68, well, I don't know why I'm not writing, 68, 90, 90, wow, I can't even remember, 68, 95, 97.9, I believe that's our rule, 99.7, I always get that wrong, 68, 95, 99.7 rule, which should help us. So if we figure out the numbers that fall between the mean and the first, second, and third deviations, we should be able to figure out if this falls fairly normal. So let me show you what I mean. So our mean plus or minus our first deviation, standard deviation. Well, mean plus or minus first standard deviation is 8.682 plus or minus 2.225. So what numbers do I get there? Well, 8.682 minus 2.225 is 6.457. So this is 6.457. 2, and if we add it to the top, we get to 10.907. All right, well, how many of these numbers up here fall in that range? Between 6.457 and 10.907. Well, 6.457 is going to start here, and it's going to go all the way Ooh, all the way down here. So quite a few. So we're going to count them 1, 2, 3, 4, 5, 6, 7, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 36. We should get 36. So I have 36, if I've typed those in properly, out of 50 that fell within this range, which happens to be 72%. All right, now let's do it for plus or minus 2 standard deviations. So the mean, plus or minus 2 standard deviations, is 8.682 plus or minus 2 times 2.225. And the range I get here is between 4.232 all the way up to 13.132. So if I count those again, so from here up to 13 to here. Well, that's pretty easy. I don't even have to count those. That's 48 out of 50, which happens to be 96%. And then our last one is 8.682 plus or minus 3 standard deviations. 2.225, sorry guys. And if we do that and plug it into our calculators, we get 2.007 to 15.5357. Now, handy for us, that encompasses everything, meaning that I really don't have anything outside of that. Hallelujah, because I shouldn't. But actually, I don't have anything above 3 standard deviations, not even 3.4. So this is going to be all of my numbers, 50 out of 50. So that's 100%. So what does this mean? Well, remember my 68, 95, 99.7 rule. Well, 72 is not far off of 68. 96 is almost 95. And 100% is 99.7, right close. So because these are all close, I would say this is approximately normal. All right, we're also going to, last little thing we're going to look at is a normal probability plot. Normal probability plots I'm not going to have you make by hand, but I do want you to see them and see how we can look at them and kind of see what they're telling us. A normal probability plot is taking data that we get from the unemployment thing we just did. We're going to arrange it in ascending order. Here's the histogram for this data. And we're going to record the percentiles. Then we're going to use the normal distribution to find the z-scores at each percentile. And then we're going to plot the x's against the z's. So right here, these are my x's and these are my z's. So it takes a lot of time. I'm going to tell you that we're going to look at this on the calculators in class. But what I want you to see is how we can use this. If the data is normal, we will get, it's close to normal, we're going to get a straight line. So you'll see that if I do this, all of this data on this normal probability plot lies right approximately on a line. So therefore, I'm going to say that this is an approximately normal distribution, which we just proved with the last 86, 90, 68, 95, 99.7 rule. So here's another one. Here's the guinea pig survival rates after they're infected with infectious bacteria in a medical experiment. Poor little guinea pig. It makes me kind of sad. All right, I'm laughing, but I am sad because, you know, they're God's creatures. All right, so here's the histogram that we've made for this survival time. Now, I can tell by the histogram this is not a normal curve. Clearly, I have some serious skewing. So we would say this is skewed what? That's right, class. This is skewed right. Now, I can also take this data and I can plot it in a normal probability plot, which I've done for you. I don't need to bother to do anything other than that because I can see that there is no way that this is even close to a line. So because this is so messed up, you can see this kind of goes up quickly goes up quickly, and then it tails off. Wow, much like our histogram. So this is not normal. And by both the histogram and the probability plot, we can see that it is highly skewed right. So today you're going to look at normal distributions, you're going to do some calculations, and then you're going to identify whether things are in fact normal or not. I hope you enjoyed this little section of 2.2, and hopefully the next video will have me in it. Please let me know if this stylus was better. I'm sorry about the writing, but hopefully it will get rid of the loud, obnoxious clicks.